Okay. So the section 6, is introducing radicals and rational exponents. You have some experience already with radicals, right? We know that the square root of 4 is 2. Kind of our most simple situation, but there's some more complicated and subtle issues that we have to talk about when introducing radicals. So that's in homework 1 is kind of an introduction to radicals. If we say the square root of a number a is equal to b, that means it means two things. It means that b squared is equal to a, and b is positive. So when we write down the square root like that, we're only referring to the positive square root. There's two numbers, right, that when you square it and get 4, but when we write down the square root of 4, that's just 2. Okay, we don't want to have a square root have two different outputs. That would make it not a function. It would make it hard to work with. And so we define the square root to be the positive one. And this is kind of a reoccurring issue with square roots, this positive negative situation. It kind of flows through the whole course of the section here. A good thing to remember is that a square root is always a positive number. So that's kind of a simple approach. But we can also have, we don't have to be limited with square roots. We can also have cube roots. When you're working with a cube root, this value here, or this number here, is called the index. Right, with the square root, we leave that blank. That's our default. It's like there's a 2 there, but we don't write the 2 because we just assume it's a square root. But if it's anything else, we have to write an index in there. And just like the other situation, the cube root of a is equal to b means that b cubed is equal to a. So the roots are defined in terms of exponents, right? So it's like we like to do in math. We base new things off of things we already know. We know about exponents, so let's define these roots in terms of those exponents. Now, we don't have the same issue with negatives and positives. The cube root of -8, that's just -2. Because -2 cubed is negative times a negative and times a negative is -8. So that works. But notice with the square root, if I try and take the square root of -4, here I actually have a problem. This should be a positive number, but no positive number when I square it is going to give me -4. And actually a negative number isn't going to work either. So at the moment, we're going to say not a real number. So square roots have kind of issues with positive and negative values. We have to be careful with them because of how negatives work. But cube roots are not an issue, right? And that's true for all odd powers and even powers. Even powers like function like square roots, and odd powers function like the cube root. Our other kind of complication here, I guess, with the square roots and the positives and the negatives is if I try and take the square root of, say, x squared. So normally we would just be able to say that's x. the square root of x squared is x, because certainly x squared is x squared, right? If you square this, you get x squared. The problem is this x, I don't know if this x is positive or negative, and I said that the square root should always be a positive number. I could write the same expression if x was negative, negative 3 squared. This would say that negative 3 squared square root is negative 3, and that's not true, right? This should always be a positive value. So if I don't know what x is, we need to add these absolute value bars. If we don't know what x is. Because we want to make sure our answer is positive. Right? If I don't know what x is, then I have to put the absolute values there to make it. Again, not an issue with cube roots, right? This is only an issue for square roots, or technically fourth roots, but we don't see that quite as often. Obviously, if I know what x is, like if x is 5, then I don't need absolute values because 5 is a positive already. Okay. I think that's sort of touching on the most tricky parts there of the homework one. Sometimes you will see, well, actually a lot of times you'll see problems that try and get out of this situation. And the way they do that is we're going to assume that the variables are positive unless they're stated otherwise. So the idea is kind of like, well, this is a sort of a pain to have to put the absolute value on it every single time. And so what we're going to do then is we're just going to assume that the variables we're working with are all positive. And that allows us then to write the square root of x squared equals x, right? If the variables are all positive, then x is positive. And so I don't need the absolute values here, right? So, and that's true for our work too. We're going to assume that everything is positive unless I say otherwise. Okay. So from there, we move into what are called rational exponents. So rational, the names are somewhat similar, which makes it maybe a little confusing. Radicals are the square roots. Rational means fraction, right? We saw rational expressions, those were fractions. These are rational exponents. So they are exponents that are also fractions. So that's sort of our framework here that we're working on. What I want you to do is try and figure out what exactly a rational exponent means, right? What it's telling us. So a fraction here. So for example, what if I look at 9 to the 1/2 power, right? It's not at all clear what that exponent really is, right? Like, what does that mean? I know what 9 squared means, right? That's 9 times 9. But what does the 1/2 power mean? Well, here's a way of figuring out what it means. What happens if I square this expression? Well, our rules of exponents would tell me I should multiply these two exponents together. So whatever this thing in blue is, I know how to work the exponents. When I multiply these together, I just get 1. So that gives me 9 to the 1, or 9. So what's in here is something that when I square it gives me 9. Well, you guys know what that is, right? What do I square and get 9? What's in here has to be 3, right? Which, if we had done a little more work with radicals, we would also recognize, right, as the square root of 9. Right, that works the same way here, so they must be the same things. So a rational exponent here is just another way of writing roots or radicals. And it has some real advantages and disadvantages, but it's really nice to be able to bounce back and forth. So now we have another way of looking and working with radicals, which are these fractional exponents. And I'm just going to start with our kind of full definition here. We don't always have to have a numerator of 1 and a denominator of something else. It can be other expressions too. So let's say a to the n over m. The denominator is going to give me the index of the root, and the numerator is going to give me just a power. So this is how I can convert from a rational exponent to a radical, or from a radical to a rational exponent. I can go back and forth between those two. Let's just see some examples here. Oh, and I guess you can also do this work in another order. You don't have to do the power first and then the radical. You can do the radical first and then the power, it turns out. And it's often easiest to do the radical first, because that's going to kind of make the number smaller, and then the exponent makes it bigger. So for example, let's look at 8 to the 2/3. It's a little bit like negative exponents in that when you write down 2/3, it feels a little weird. Like, what does that mean? So we like to change it. We like to put it into a better form first. So this 3 is going to be the index. And then the 2 is going to be the power. Notice I wrote it in the second form because I know the cube root of 8. So I really want to do that right away. Cube root of 8 is 2. And 2 squared is 4. Right? Cube root of 8 is 2 because 2 times 2 times 2 is 8, right? Because of the radical is the same as a expression, right? The radical can be rewritten. Okay. I mean, we could do some others like this, but they're pretty similar. How about 4? Well, we get a little limited here, but 4 to the 5 halves. You just got to remember the denominator is the index. So, maybe you write that in here in this case, even though we don't normally write in a square root, just to keep track of where those parts are going. Square root of 4 is 2. 2 to the 5th is 32. Okay. So, this is one way of working with fractional exponents, just kind of evaluating expressions. You will also see some problems in this section that ask you to simplify rational exponents, and that's just using your same old exponent rules that you would have used before in previous sections, and you would then apply those to these fractional exponents. So, for example, let's try 2x to the 1/3 squared all over x to the 2/3 times x to the 1/2. Okay. So this is very much like what you've done with previous exponent problems. It just happens that the exponents are fractions. So it's a little bit harder to work with, right? Because fractions take a little more effort. But it's a very similar process. Here I'm going to distribute that exponent to both of these pieces. 2 squared. Here I'm going to multiply 1/3 times 2. That'd be 2/3. Well, I actually made this problem maybe easier. Right? Normally I would add these two together and I have to get common denominators because I have to add those two fractions together. But I have an x to the 2/3 and an x to the 2/3 on the top and the bottom. So that gives me a 2 squared over x to the 1/2. Let me just show you an example of if you have an expression like that, x to the 2/3 times x to the 4/5. There, when you're multiplying those like bases together, you add their exponents together. So this is going to take a little bit of work, and maybe I just want to do it on the side down here, right? I need common denominators. I'm going to multiply here by 3 and here by 5. 10/15 plus 12/15 is 22/15. And normally when we start a problem, if it has rational exponents, I normally just leave my answer with rational exponents, like this. I would only change it to a radical if the problem actually asked me specifically and said write it as a radical. And I can do that, 15 x to the 22nd. If the problem doesn't say write it as a radical, then you're welcome to leave it in whichever form you prefer. But there's no reason to change it unless you're forced to, right? So sort of stick with the form that's given and you can move from there. Any questions on these rational exponent problems? Okay. Okay, 1 second. Okay, I'm back. The last section I wanted to make sure to go over with you is how to simplify radicals. And I find this maybe the most important of the sections. Without this, it's very hard to do any of the later homework assignments. And it sort of leads to problems throughout all the work with radicals. Some of the other things you can do or not do successfully and you can still get the other stuff right. But simplifying radicals is something that really runs throughout most of the work we do, even through the rest of the semester. All right, so this is a real section to put some time in and make sure you feel really good about this section before we move on to the other sections. And the idea behind simplifying radicals is that some radicals are very easy to simplify, and we've seen a lot of these already, right? The square root of 9, well, that's just 3, right? And we would want to simplify that. We would never want to leave it as the square root of 9 because it's much nicer to write it as 3. But what about if I have the square root of 12? So the problem there is that this is not a square root that I can find directly. There is a number that's the square root of 12, but that number is a decimal, and that decimal repeats, or it goes forever and it never repeats or stops. It's called an irrational number. So it's a complicated, in our world, we feel like it's a complicated thing. And so this is something we can't do the same way I did the square root of 9. But there is a way to simplify it to make it better. And the strategy for that is to recognize that if I take a square root of a times b, I can rewrite that by taking the square root of each of those pieces separately. And this is really actually a result of radicals. I'm sorry, of rational exponents, right? ab to the 1/2 is a to the 1/2 times b to the 1/2, right? And that we know that from our work with exponents, and a radical is just an exponent. So this is really not that amazing. It's just like what we did here already, just with a fractional exponent. Now, the question is, how does it apply to this situation? Well, in order for this to work, I need to factor what's inside. And you can factor 12 in a couple ways. You can do it 2 times 6, but that's not very helpful. A much better way is to factor that as 4 times 3. Because now I know the square root of both of 4. I don't know the square root of 3. That's not a perfect square, but the square root of 4 is 2. So I can rewrite this as 2 square roots of 3. And this is a simplified version of 12. And it's simplified because I have less stuff in the square root, right? That's my goal, really, is to pull as much out of the square root as I can. I'd love it if everything could come out of the square root, but many times that's not possible. So I'll just pull out what I can. So I'm looking for what I call these perfect square factors, right? And, you know, if you don't, you probably know many of these already, right? But the perfect square is 4, 9, 16, 25. Etc. Right? Those are going to come up a lot for us, so just be very comfortable with those, or look for those with these problems. Okay. Let's try another example. Let's look at the square root of 48. So what I do when I see a number like this is I say, well, that's not one of my perfect squares here, right? It's just a little bit off, right? I know it's something close to 7, right? The square root of 49 is 7, so this number is close to 7, but it's not exactly it. So I want to simplify it. What I want then is a factor here that goes into 48. If there's no perfect square factors, then I can't simplify it and I just leave it. But there is in this case. And so you might look at this and say, I can see 48, that's 4 times 12. And that is a good start because 4 is a perfect square. And so this can be reduced a little bit, but there's more. You've missed another perfect square factor here in the 12. The easiest way is to recognize that 16 is also a factor, right? 48 is 3 times 16. But you could also write 12 as 4 times 3 and simplify it here in 2 stages. So either way, you're going to get the same answer here. This is going to be 4 square roots of 3. This is going to be Square root of 4 is 2. Square root of 4 is 2. Square root of 3. So that's also 4 square roots of 3. So we want to make sure to pull out as much as possible from the square root. We don't want to leave any perfect square factors inside. This also is true when we are working with variable expressions as well. So let's say the square root of 3x to the 5th. Let me make that 3x to the 8th.
Where's the cave? Meet me at the treehouse.
3x to the 8th.
I'm in the treehouse cave.
So when I look at this, I want to look at the perfect square here. Now it's a little tricky because this is x to the 8th. It's 8 is an exponent here. It is not a coefficient. It's an exponent. So it works a little differently than these numbers here. I'm not taking the square root of 8. This is working like an exponent. The 3 here is not a perfect square, so that part's going to stay inside. So I'd actually kind of start to kind of flip it around because I'm thinking that the square root of 3 is going to stay inside. When I'm working with exponents, I want to remember that the square root is really a fractional exponent as well. So when I take the square root of x to the 8th, I'm really applying a 1/2 exponent, which is going to divide this exponent in 2. So that's going to be x to the 4th times the square root of 3. And that sometimes is tricky for students because you have both a, you're working with the number where you're taking square roots, but then you're also working with an exponent where you're using these sort of 1/2 powers. And so we want to be able to do both of those. And I personally think it's helpful to be able to kind of switch back and forth. So let's see another example of that. I'm not sure this one that we just did was the best. Let's try the example 18x to the 5th. So what I'm going to do here is try and break this into 2 parts. My first part are like the perfect square parts, the parts that I'm going to be able to take the square root of. And the second half are going to be the parts that are going to get left inside the square root that I can't do anything with. So I'm going to start with the numbers, 18, and 18 is best broken up, right, as 9 and 2. So 9 is the perfect square part. That's going to become a 3. And this 2 here is going to stay within the square root. It's going to give me a 2, like that. Okay. So then my next part is to do the same thing with the x's. And here, remember, the square root is a 1/2 power. So what I need is an even x. X to the 5th isn't going to work, but x to the 4th certainly would work. X to the 4th times x is x to the 5th. The square root of x to the 4th, remember with the exponents, I'm going to divide 4 by 2. That's going to give me x squared. And that x is going to stay inside. Any questions on these? I'll do a couple more examples, but my experience with teaching this is a process that for many students in the beginning, it feels a little kind of, should we say crazy? Like, okay, where are all those parts going? But once you get it, and once you see how the things are being broken up and put together, it's a very consistent process, and that students do quite well with it. But there's a big divide there, right? Of like, I have no clue what's going on, and the numbers are just floating around randomly, and I understand why these parts are going in the right places. And if you can get on the good side of that divide, you'll do pretty well overall in this whole section. But if you're on the wrong side of that divide, like all the problems just feel very random and arbitrary, and we don't want that to happen. So we want to make sure that, I'm hoping that these examples are helping you see kind of the choices that I'm making that are then leading me to these proper answers. Now, what about this? What about the cube root of 24? This is the way math goes, right? You feel maybe like, okay, I'm kind of getting this part, and then all of a sudden it moves on to something else, right? Something different. But our goal is to help you see the similarities, and there are a lot of similarities here. We don't want to get stuck in a pattern that's inflexible. We want to be able to see the structure of it, but that gives us a flexible pattern to apply. I can bounce back and forth and do new ones that I haven't seen before because I understand the pattern. So here, because it's a cube root, these numbers are of no use to me because I can't take the cube root of any of these. What I want to do instead is think about what my perfect cubes are. So my perfect cubes are going to be 2 cubed, which is 8, 3 cubed, which is 27, 4 cubed, which is 64, 5 cubed turns out to be 125. You probably won't see that one very often or anything bigger than that. And most of the time you'll be working with those. The numbers just get pretty big otherwise. So knowing that, we can break this apart the same way, but I don't want to factor it as 4 times 6. That was like that would be work well for a square root, but not for a cube root. For a cube root, I want to factor this as 8 times 3. So the cube root of 8 is 2, and the cube root of 3, I leave alone, right? I can't do anything with that cube root. Example, let's try the cube root of x to the 10th. Okay, so remember here when we have an exponent, x to the 10th, I switch gears, right? I'm not looking at these cube roots because with exponents, this is going to function as a 1/3 power. So it's going to divide this exponent by 3, and I want that to go evenly. So x to the 10th doesn't go evenly, so I have to break this up. This is going to be the cube root, and I want to break it up so that I have the largest. I mean, you could write it as x to the 3rd and x to the 7th, but that actually wouldn't be that great because there's a lot of perfect cubes in that x to the 7th. I want to break it apart so that I have the most perfect cubes, and the way to do that is to do x to the 9th and x. So this is the largest part that's still divisible by 3. And then I have this little leftover part. So the cube root of x to the 9th, I do that by dividing this exponent by 3. That's going to give me x cubed. And then I have the cube root of x. Okay. Any questions on these? It's like I said, if you can do these problems, you can then certainly do harder problems. I have confidence. And also, this will provide the foundation for the later work and later homework that you have to do in this section. Okay. So again, make sure you get this homework 3 down and feel good about it before you move on. And please ask me if you run into any trouble with these. Okay.